Hello everyone. Thank you Arun for inviting me for this talk. So I'm Ravi Gautam. I'm working with Professor Prabhu Nott on the static granular media. So today I will be talking about stress in a static granular column. Granular materials such as sand and food grains have been studied for long, but their mechanical behavior can still surprise us. So one simple example is this, where the stress, and if you fill a column, granular column, and apply stress, the stress on each particle is not same. There is a very large stress heterogeneity exists in the system. So today I will be talking about one simple example of this complex system. And so before starting this, I will set up the basics, how I simulated this and the basic terminology. So first, the simulation. So in granular materials, we need to track the motion of each particle. For that, all we need is the Newton's law of motion. But the interaction between particles need to be simulated, and we use spring and dashpot model for that. So there are three parameters in this model. One is the particle stiffness, which because in our model we treat the particle deformable, so there will be some stiffness associated with this deformation, and the coefficient of restitution, which means basically the inelasticity of the collision. The collisions are not elastic; they lose energy when the particles collide. And another parameter which is interparticle friction coefficient. So most of the particle in reality in experimental on or industrial systems are frictional in nature. From this simulation, all we get is the position and velocity of all the particles. So this is a simple way to describe the simulation. From the position and velocity, from the position we can construct the network. In a static media, the particles will be in contact. So from the position, if we can figure out the two particles are in contact. If the distance between their centers are less than the sum of their radius, which means that the particles are overlapping and they will be in contact. So we connect those particles in contact with the edge, and we treat the center of the particle as node. So we get this network. We can also include the contact force information in this network by setting the length thickness of the edge equal to the contact force. So we call this contact network, and this is force network. One term which I will use here is coordination number, which basically means the number of contacts of a particle. So we can calculate this coordination number from here. Now moving on to the problem I'm presenting here. So start with a simple case. So let's fill a vertical column with water, and we measure the normal stress or pressure on the wall. We all know that it will be a linear profile, our standard rho g y, where pressure on the wall will increase linearly with the depth. If we do the same thing in somewhere in space where gravity is 1/3 of the Earth, the profile will still be linear, and at any point the stress will be divided by a factor of 3. But if we scale this sigma n or normal stress by the gravity scale, both these profiles will overlap. But if we replace this granular column, we replace this water with a sand, the things changes. There are two observations here, two important observations to make. The first thing is that stress does not grow linearly anymore; it saturates after a depth. And again, if we scale it here, all the profiles does not collapse. So based on these two observations, there is a very neat there is a very clear trend here. As we reduce the gravity, we are increasing the saturation length. So earlier the Johnson model, which considered the average over the entire cross section and estimated the normal stress at any depth. As per this model, all these profiles would have been collapsed, which does not happen in the DM simulations. I have observed a similar trend if we fill the particle with another stiffness. So the trend is very same here. Increasing the stiffness has the same effect as decreasing the gravity. So it is clear that the Hansen model is not able to capture this feature. So what is missing in that model is the microstructure of this packing. Somehow we need to incorporate the microstructure. We need to characterize it in a way that we can use it in a continuum model. So today I will be presenting about how to characterize it and what does it actually mean and how it changes. So in this slide, I will basically talk about the basic features of microstructure. So we generate a packing from the DM simulations. We divide it into a small grid, and we look at the contact angle at each grid. So this is just some 2 particle diameter by 2 particle diameter grid. and there are some hundreds such realizations. So we have enough number of contacts in each grid to make some statistical averaging. So each contact will have a two values. One is the orientation, its orientation, which I am measuring from the vertical, and the contact force. So we can plot the contact angle distribution in each of these grids, right? And we can say there is just a mean. We can clearly say that this is anisotropic. So we can estimate a mean orientation in this grid point, right? We can also estimate a weighted mean where we can also include the information of the contact force. So where I'm calculating the weighted mean, where the mean is taking the contact force as a weightage. All right. So even these two are not sufficient to adequately characterize the anisotropy in the system. This gives the angle of anisotropy. It does not tell anything about the magnitude of anisotropy. So for that we need, use this function to fit this distribution, where the A become now A is basically now the magnitude of this anisotropy. Right. So to understand it better, let's say there are these three kind of contact angle distributions. All of them has a anisotropy, angle of anisotropy theta naught, that is 0 here in this case. But the three are very clearly different profile. The blue one is perfectly circular here, so there is no, this is isotropic medium, and these two are anisotropic. They differ by this value A here. So A increasing from 0 to 1, we are more growing to, we are becoming more anisotropic system. So from this analysis, there are three parameters which I am defining to describe the anisotropy. First one is the mean orientation and the weighted mean orientation, and the anisotropy, which I am for now averaging over the entire system. Okay, so we do the same thing for the each of the grid point. At the end, we get a, theta bar and theta w bar vector field in this case. So to understand this better, how does it actually look like? We have a theta bar at each point. We connect them as similar to a streamline like in a fluid, and we get this kind of profile, which means that as we moving closer to the wall, there are more contacts towards the wall than the opposite side. And the force line suggests that the weight of each grain is actually not, moving vertically, it is more inclined towards the wall. So that's how we get a stress saturation on the wall. The weight of each particle is, there are more contact along towards the wall, so it is shifted towards the wall. This was the simulation results, and there have been never experimental validation of the anisotropy in the static system. So we tried to do experiment with photoelastic materials. Granular materials are really, difficult to do particle scale measurements. So photoelasticity is one such approach where we can actually measure the contact force. Okay, so it is a simple system where we emit light from a source and we put two polarizer, horizontal and vertical polarizer. At the end, we don't see any, we see a black screen. If we put a particle and we apply some force, we can see some specific pattern which gives us the contact force. So now we can take images and get this picture. We need to back calculate this contact force, what was the force there. So I have carried out this experiment and I have captured these two images. First one without polarizer and then the with polarizer. So from these two images in the MATLAB, I have identified the particle center and the radius. And then we can say that there is some cutoff. If the periphery has some 10 pixel diameter gap, we can say that there is a probable contact. Then we will extract one particle at a time and then optimize the three contact forces. We will know that there are three possible forces from this network. So we'll optimize that and we will get a contact force. So we generate a synthetic image and to see that these two are looking similar. And now we can generate a force network similar to the DM simulation. So we generated the force network from the experiment and then I estimated contact line and force line following the same procedure that I have followed for these DM simulations. There is some difference in the qualitatively the DM and the experimental results are matching, although there is some quantitative difference. I have done these experiments for two different kind of geometries. One where the wall are basically replicating made of a particle, and another one where the wall were smooth. So these are the contact line and force lines of different cases. So as we can see that the lines for these smooth walls are slightly less inclined, the anisotropy is low. So after that we can say that the anisotropy is actually real. It exists in the experimental system as well. We move back to simulations because we can do simulation for a range of particle, range of stiffness, and the friction coefficient. So here, if we say that if we increase the friction coefficient, the saturation length is actually decreasing. But if we increase the stiffness, the saturation length is we increase the stiffness, saturation length is increasing. So in both the cases, although the mean coordination number is decreasing, it has a opposing trend, which can be closed if we plot it in terms of mean anisotropy in the system. Yep, next slide. So if we mean anisotropy in the system, so all the simulation I have plotted it in a single plot. As the anisotropy decreasing, our length scale will increase. So to conclude this talk, so as we know now, granular material network in a static column static granular anisotropic, and the anisotropy depend on stiffness, friction coefficient, and wall. And the anisotropy single-handedly governs the stress saturation in a silo. If there is no anisotropy in the system, we expect that there will not be stress saturation. And now I'm planning to do some experimental measurements of stress on the wall for different particle stiffness and see that there is actually a change in stress saturation length. Thank you. That's all I have.